Hi everyone. So we're going to be talking about exponential growth and decay questions. Um, these are word problems that either we would look at them and they would be growing really fast or decaying really fast. That's why they're considered exponential. So before we get started with the examples, I wanted to go over the exponential growth decay equation, which is right here. It's y is equal to p times 1 plus or minus r to the power of t, where y is like our answer or what we want. And then p is our starting population or starting amount. Because we can use these exponential growth equations for populations, we can use them for money, we can use them to find like how high a ball bounces. We'll go through a bunch of examples so I can show you. And then our R stands for the interest rate or the rate at which it's growing or decaying. And then T stands for time. So the other thing I wanted to tell you is that this equation has a plus or minus. Now, it's not that you have to do it twice. You don't have to do the plus and the minus. You get to choose. So if it's growing, if you read the equation and you know it's growing, we use the plus. If you read the question and we know it's decaying, then we use the minus. So on these examples, we have to decide if it's a growth or a decay problem, and then we use the equation. So let's start with the first example. I'm not going to write these questions down, but I will read through them and then write down the important stuff. So the first example says a savings account balance is compounded annually. If the interest rate is 2% per year, so that's going to be important. And the current balance is 1,520. That's important. What will the balance be 9 years from now? So 9 years. Like, what is it in 9 years? Okay. And it says round to the nearest cent. So this is actually all the information we need. So what we're going to do is first of all, let's decide if it's a growth or decay problem. Usually with money, unless it says so, it's growing. So when we put money into a savings account, it gets bigger and bigger and bigger. So we know it's a growth equation, which means we're going to use the plus sign in our equation. So y is equal to, the y is what we're wanting. We don't replace the y with anything. We're solving for y. And then p is the starting amount. So that's the amount that we currently have, which is 1,520. So I'm going to replace the p with 1,520. Then in the parentheses, I'm going to have 1 plus, because we decided it was a growth equation, not minus. And then your R is your rate. That's usually a percentage, so we know it's a 2% interest rate. Now here's the deal. We don't just put 2 in there because it's a percentage. To convert between percentages and numbers, we have to divide by 100, which is like, so if I do 2% divided by 100, that gives me 0.02. You could also write just 2 over 100 or whatever your percentage is over 100 in here. It does not matter because you're going to plug it into a calculator anyway. And then your T stands for time, or how much time we're going to let it sit there. We're asking what the balance would be in 9 years. So I'm going to replace the T with 9. Okay, now we're just going to plug that into a calculator and make sure that you put the parentheses in where we have them. And what I get is that y is equal to 1816.54, which means, and I should put the dollar sign on here, so let me do that. That means that if we have $1,520 with a 2% interest rate, in 9 years, you're going to end up with $1,816.54. Okay, let's go to the second example. And before I read it, I'm going to actually move this equation down so that we can use it. Okay, so let's read the question. For tax purposes, a rental car company assumes each car in their fleet depreciates by 9% per year. if the initial value of the car, okay, let me backtrack and write this. So we know it depreciates by 9% each year. If the initial value of the car is $38,000, what will the value be when the car is 8 years old? So the 8 years old has to be our time, right? The $38,000 is the original amount, and the 9% per year has to be our rate because that's the percentage. Now, what we have to decide if it's growing or decaying, because it uses that word depreciates, that means it's decaying. Cars don't keep their value, they lose value, so we're going to use that minus instead of the plus. So I'm going to say y is equal to our starting value, which is 38,000. Then it'll be 1 minus, because it's depreciating, the percentage rate, which is 9% per year. So to do 9% in decimal form, it's 0.09 to the power of t, which is 8. Now let's plug that in, which would give us 17,869.60 when we round. So what that tells me is that if I have a $38,000 car and I drive it and I use it for 8 years, then want to sell it, I could sell it for $17,869.60. All right, let's go to the next question. And once again, I'm going to pull down this equation so we can keep on using it. Okay, so the third example says, a philanthropist pledges to donate 12% of a fund each year. If the fund has $30,500 in it, so in 2020, how much will the fund have in 2031? So this one doesn't give us the amount of years, but it tells us that we started in 2020 and then we wanted to go to 2031. How many years are between 2020 and 2031? There's 11 years. So that 11 years is our T. The 30,500 is the amount we start with, so that's our P, and then the 12% is our R. So the next thing we have to do is decide if it's growing or decaying. When we're donating something to a fund each year, it's growing, which means that we're going to use the plus sign. So I'm going to have y is equal to my starting amount, which is 30,500 times 1 plus the rate, which is 0.12. That's 12% as a decimal. Once again, we could have written like 12 over 100 if that makes more sense to you. Totally up to you. To the power of t, which will be 11. So let's plug that into my calculator. And I end up with, let's see, $106,095.77. Sweet. Okay, last example. All right, a rubber bouncy ball is dropped from a height of 115 inches onto a hard flat floor. So 115 inches. After each bounce, the ball returns to a height that is 20% less than the previous maximum height. What is the maximum height reached after the 7th bounce? Okay, so here's the deal. This one's a little bit different because we're not dealing with money. But the 115 inches is like the starting height. So we're going to use that as our starting amount. The 20% is your rate, and then the 7th bounce is actually your time. Well, I realize that 7th bounce is not necessarily a time. We're going to use it as the time in this question because it's asking what happens after the 7th bounce. Now we have to decide if it's growing or decaying. When we bounce a bouncy ball, it should slowly get smaller and smaller and smaller, or the bounce height gets smaller and smaller and smaller, which means that it's decaying. So we would use the minus sign instead of the plus. So when we write our equation, we're going to have 115 times 1 minus your rate, which is 0.20. Once again, that's 20 over 100 to the power of 7, because the 7 is going to be our t. So when I plug that in, I'm going to end up with 24.1. And so that's not money, that's in inches, because we started with 115 inches, and then after 7 bounces, now it's only 24.1 inches high. Okay, and there we have it, how to use growth and decay models.